Okay, so now we're going to talk about the parity algorithm for determining whether you're in the interior or exterior of a closed polygon, right? Okay, and of course the basic idea it's like of trying to do this is that we're going to try to find it's like algorithmic approach to the problem of whether you're in the interior or exterior it's like of curve, right? So if you want to approach this computationally, of course, then one way to do this is to replace the it's like the curve it's like with some sort of polygonal approximation, right? So to approach this computationally, right, we replace, you say your Jordan curve, gamma, right, by a polygonal approximation. And then you ask how we can determine whether or not you're in the interior or exterior, it's like of a closed polygon. If a given point x is in the interior or exterior of a closed polygon. Okay. All right. So the basic idea, if you will, the parity algorithm is the following. Imagine you have this kind of polygonal domain, so a closed polygon, if you will. Okay, say that. All right, and then say I have a point here, x, okay, and I want to tell whether I'm in the interior or exterior of this. So modulo issues of whether or not, it's like you're in what is called general position. We're going to sort of think about this pictorially. So you take a point x and you sort of draw a line, half line out, okay, to infinity, and then you count the number of times you cross the polygon, okay? And so the idea, it's like, which you can easily convince yourself of, is that if you cross the polygon an even number of times, then you are in the exterior, and if you cross it, if this half line, it's like only crosses the polygon a sort of even number of times, it's like you're in the exterior. It's like if it crosses an odd number of times, you're in the interior. So it's called a parity algorithm because in some sense you care about whether or not number of crossings is odd or even. Okay, so all right, so that's sort of pictorially, it's like what's going on, and of course it's like it's like this breaks down to a simpler problem, which is that if you have a point and you have the two sort of nodes, it's like which associated with a particular edge, it's like you want to ask whether or not that half line is going to intersect that edge. Okay, so we're going to reduce this problem to asking, it's like given it's like a particular edge, it's like whether that half line crosses that edge. Okay. So, all right. So to simplify this discussion, is like we're going to assume several things. We're going to assume that that half line is horizontal, right? So it's somehow aligned. It's like with the x sort of direction. It's like of your coordinate system, and we're also going to assume it's like that these 3 points are not collinear, and we're also going to assume that any of those 3 points, it's like they don't either share a horizontal vertical component. Okay, so there are a bunch of assumptions it's like which are built in, and generically, it's like they will be satisfied, and if they're not, the idea, if you will, is that you can perturb it's like that point slightly so that they are satisfied, or maybe it's like you might have to rotate the polygon slightly. So we're not going to worry too much about that. It's like suffice to say, in order to actually implement this algorithm in a robust way, it's like it requires a little bit of work. It's like to make sure that you don't encounter these non-generic situations, or you can get out of them. But let me just sort of address the basic idea in the generic case. So let me state sort of the assumptions. It's like which are implicit in this, right? So to simplify the discussion, right? We assume that the half line is horizontal. No 3 points. Okay, so the 3 points are not collinear. And no 2 points share either a horizontal or vertical component. And then it's like one further assumption. So let me sort of draw that picture. So imagine you have the point X here, and you have a point A and B. It's like which denotes that line segment, okay, or that edge, and then that sort of line emanating sort of to plus infinity is the half line, okay, and then we're going to assume A is on top of B, right, and the point A is above B. Okay. All right. So those are sort of the assumptions it's like we're going to make. Okay. So all right. So let's see what happens. So of course, in order to implement the parity algorithm, what we're trying to do again is to try to determine it's like whether or not there's a crossing for a given edge segment and that half line. Okay. So so we first check. So we check that you actually have this kind of thing, right? So you want that A2 is less than X2 is less than B2, all right? And then we compute and of course if that's not true, then you have to swap it, okay? Yeah. Then if that's true, then you can compute a determinant that's like of this following 3 by 3 matrix, okay, involving X, A, and B. Okay, so this is the determinant of this matrix: 1, X1, X2, 1, A1, A2, 1, B1, B2. So, so you probably know it's like amongst other things that the determinant tells you something about the handedness. It's like or the orientation, if you will. It's like of the you know, it's like the parallelepiped, it's like which is generated, it's like by 3 vectors. Okay, so that tells you in some sense whether or not there's a left or right-handedness, if you will, to this. Okay, so it turns out that if you're choosing this sort of positive ray, right, that you have a crossing if this determinant is positive, otherwise you don't, right? So which is positive if there is a crossing. Okay, so that leads to the following algorithm. Okay, so the algorithm is that, and it returns a Boolean, which is true or false. And so it asks the following question: does you know, the line segment AB cross this half line from emanating from X? Okay, so it does cross AXB, and then first you check this orientation condition. So if not A2 X2 B2, right, A2 less than X2 less than B2, right, then you return false. And then otherwise, it's like you return whether or not that determinant is positive. Otherwise, you return whether the determinant of this matrix okay, so that's all there is to it. Okay, and then what you do, of course, is that you run this dust cross thing for every edge in order to give you the number of crossings. Okay, so running this for all edges gives the number of crossings, or you count the number of times. It's like that thing returns a true statement. Yeah. And then modulo these potential issues about sort of non-genericity, right? So suffice to say, it's like in practice, in order to implement the parity algorithm in a robust way, it's like does require a little bit of thought and care. Okay, so but at least the basic idea it's like is not so complicated. Okay, so so let me just stop here for now.